Hello everybody, I am happy to see you again. Today, we will talk about gear trends and how to compute their gear ratios. In general, gears are of interest to designers only when they are used in pairs as motion and force transducers. These gear pairs can be combined in many ways to achieve desired input over output relationship. A combination of one or more gear pairs that are integrated is called a gear trend. All complex gear trends are combinations of the simple gear trends, compound gear trends, and planetary gear trends. This chapter will talk about how to determine the gear ratios of these three gear trends. We can determine the gear ratios of planetary trends using the equation method and the tabular method. However, we only talk about how to use the equation method to compute the gear ratios. We will skip section 13.4.1 for concentric gear trends. And I think the equation method is better than the tabular method for analysis of the planetary gear trends. So I skip section 13.5.3. If you're interested in this method, can you learn by yourself from the textbook? This slide shows you three types of gear trends: simple gear trends, compound gear trends, and planetary gear trends. In a simple gear trend, each shift will have only one gear. In compound gear trends, a single shift may have several gears attached. Compound gear trends typically have one input but can have several outputs. The axis of each gear shift is fixed to the frame. Planetary gear trends have one or more gears with axes that move relative to the frame. We call these gears planetary gears. As discussed in Chapter 11, the velocity ratio for two metric gears 2 and 3 is R equal to the ratio of angular velocity omega 2 over omega 3, the ratio of radii R3 over R2, and the ratio of teeth numbers N3 over N2. We also call R the gear ratio. Two external gears will rotate in opposite directions, so R is negative. An external gear matches an internal gear will rotate in the same direction. R is positive. When pair gears are involved, the angular velocity must be treated as vectors. A relatively simple way to do this is to recognize that at the pitch point location, knowing a curve and the velocity at the pitch point on both gears is the same. From this, the direction of rotation can be inferred from the simple velocity relationship. Velocity Vp2 is equal to Vp3, so omega 2 cross R2 is equal to omega 3 cross R3. The direction is shown in this figure. For pair gears, the large end of the gear is used for the measurement of the pitch radii. This slide shows you how to identify the hand of the gear. If our left hand thumb is following the inclination of the tooth of gear, the helical will be turned as the left-hand helical gear. If our right hand thumb is following the inclination of the tooth of gear, the helical will be turned as right-hand helical gear. And this slide shows you how to identify the direction of rotation for crossed helical gears. When crossed helical gears and wound gear pairs are involved, the process becomes a little more complicated because of the hand of the gear. To determine the direction of the pinion relative to the gear, we treat the pinion as a screw and the gear as fixed. Observe the motion of the pinion relative to the gear as the pinion is rotated, and the gear is built along the gear axis. If the pinion appears to advance toward the gear when the pinion is rotated, in reality, the gear will rotate counterclockwise direction. If the pinion appears to withdraw from the gear when the pinion is rotated, the gear will rotate clockwise direction. We can see this animation. The right-hand wound gear appears to withdraw from the gear when the wound gear is rotated. The gear will rotate clockwise direction like this. The number of threads in the wound is equivalent to the number of the teeth in the gear. Thus, a one-thread wound is equivalent to a one-tooth gear. Two threads is two teeth, etc.